Welcome to lesson 6.2, addition and subtraction of vectors. So far we have identified that a vector measurement is one that includes magnitude and direction. So we know the force that's being acted upon an object and the direction in which that force is being acted to or from. So I have a simple diagram here. Let's suppose you went for a walk. You walked 800 meters due north. Then you took a 90-degree turn to the left and you walked 600 meters to the west. If we wanted to draw a vector that represents your displacement, we would end up having a vector going from the start to the finish of your walk. And you can see that since we're in a right angle triangle, we can use pretty simple trig. You can use SOHCAHTOA or you can use Pythagorean theorem to figure out the magnitude of this vector and the direction of this vector. The result is that you would have walked at an angle of north 37 degrees west for 1,000 meters. This purple vector would then represent your displacement, and what it is the addition of the red vector and the blue vector. Okay, so vector addition ends up looking a lot like geometry and uses trigonometric skills. And so we're going to be doing a lot of that in this lesson. Now, vectors can act on an object in a variety of different ways. And some of them, we apply a parallel force, and sometimes force acts on an object in different directions, which then requires a couple of different strategies. But you don't have to write all this down. It's just a quick introduction. But let's say, a vector, a force like that pushes an object, and a force like this pulls an object. Well, it's pretty simple to see that we're just going to add up those two vectors, and we'll get the resultant. The resultant vector is the addition of two or more single vectors. So I'll just write that here for this purple one. This is called the resultant. Back down here, we could also apply parallel force, both behind. Even though these vectors represent a different magnitude, they're heading the same direction, so we would end up just adding those vectors together to get the total force being acted upon the object. Well, what if they were pulling instead of pushing? Same thing. Since it's parallel vectors, you add them together. But then we start to get into some more interesting things where, let's say, one vector is acting on the object with a force of 100 newtons heading this direction, and the other vector is it's pulling on the object with a force of 120 newtons in this direction. Well, then we start to get into some geometry, and we'll learn about those things, tackle those things in the rest of this lesson. All right, we're going to first consider vector addition and some strategies for working here. And we have vector A and vector B, and we're going to think about vector A plus vector B. Okay, and one thing that we can do in order to figure this out is we can just draw vector A, and I'm trying to copy as best as I can here. And what I can do is I can translate vector B so that the tail of vector B is touching the head of vector A. So I'm just going to take this whole vector and shift it so that the tail of vector B is touching the head of vector A. And now what I would have to do is simply find the resultant by drawing from the tail of vector A to the head of vector B, and I've created this new vector called A plus B. That is the resultant vector. Okay? Now, this is called the tail to head method because I've taken the tail of B and I've translated it to touch the head of A. So this is tail to head. Tail to head. Or triangle method. We've simply created a triangle here. Okay, that one's really helpful, especially when you just have straightforward vectors and they're both somewhat heading the same direction or something like that. it's when there's two vectors, that's what you would do. And you'd create a triangle, and then you'd use your trigonometry skills to determine the direction and magnitude of the resultant vector a plus b. Now, another method that we can think about and that we can use is called the tail-to-tail method. So in the tail-to-tail method, instead of translating the tail of b to the head of a, I'm actually going to translate the tail of b to the tail of a. So it's going to look, there's our translation arrow. I've got a plus b, and my diagram is going to look a little bit like this now. So I've got vector a. Again, I'm copying as best I can. And then I'm going to take the tail of vector b and start it right where the tail of vector a is. Okay, so now we kind of have that picture where, let's say there's, you know, an object here, and I've got a pulling this direction and b pulling this direction. We need to determine what the total force is. Something like that would be an example of vector addition. So here's what we do. We simply complete the parallelogram that has vector a as one set of sides and vector b as the other set of sides. So all I need to do then is draw a parallel vector, vector b, okay, right there. And I've got a parallel vector to vector a right here, okay. So I can call the parallel vector to vector b, let's just call it vector v. And now what I've indicated is that a plus b is actually the same as a plus v using the triangle tail to head method. Okay, so we've used our parallelogram, our tail to tail parallelogram, to create a tail to head situation with a plus v, and we have the resultant vector here, a plus v. And because v is parallel to b, a plus v will be the same as a plus b. So again, this is called tail to tail, tail to tail, and we end up with a parallelogram. And the resultant vector then is the diagonal of the parallelogram, starting from where the two tails originated. From here, we take a quick note on adding parallel vectors, adding parallel vectors. And it's really the same strategy. Let's say we had vector A, and we know that this is something heading 5 kilometers per hour east. And we have vector B, too long, heading 7 kilometers per hour east. Okay, so these are clearly parallel. They're heading the same direction, but they are different vectors. They have a different magnitude. So how do we add these together? Well, we really just use the same strategy, this tail to head method. So we're going to take the tail of B and stick it onto the head of A, translate it onto the head of A. And what you end up with is, here's my copy of A, and we're going to take the tail of here and translate it onto the head of A, which really just brings B right here. And they're both heading the same direction. We have 5 kilometers per hour and 7 kilometers per hour. And so we would add those up, and the resultant vector would simply be the same as triangle method, but what we've created here is a straight line. So my resultant vector, a plus b, is simply 5 plus 7. It's 12 kilometers per hour to the east. So the resultant vector, a plus b, is 12 kilometers per hour east. Nothing too difficult there. So a parallel vector having the same direction, all you have to do is add their magnitudes, and the resultant then has the same direction as the original vectors, okay? Well, what about adding parallel but opposite vectors? Parallel but opposite vectors. Adding parallel but opposite vectors. All right, so we have a situation maybe where we have vector C, and vector C is 37.5 northeast. And then we have, 37.5 newtons heading northeast. And then we have vector D, which is 15 newtons heading southwest. Okay, so if we had our cardinal, our compass here, we'd notice that northeast is right and southwest is right. Okay, those are clearly opposite directions. So we do have opposite directions, and yet they're parallel to one another. So, well, what do we do when we add these up? If you follow the same idea of what we did here, tail to tail, you simply end up with vector C heading northeast, and then we're going to bring the tail of vector D to the head of vector C, and you're going to go backwards 15 newtons, where you went forward 37.5 newtons. Okay? Well, what does that tell us? It's really just a subtraction here. To find C plus D, we're going to place the tail of D at the head of C, and then the resultant is the vector from the tail of C to the head of D. So now the resultant vector, the addition vector, comes from here and ends here. Okay? This is the resultant vector, C plus D. It's like adding an opposite, right? Adding a negative number. The number is going to get smaller. It's the same as subtraction. So the resultant ends up being 37.5 plus negative 15, which is 22.5 newtons. Which direction? Well, still overall it's heading northeast because the vector heading that direction had a larger magnitude, okay? So really what we're seeing is that the magnitude of the resultant is equal to the magnitude of C minus D, and the direction is the same as the direction of C. And this is as a general rule. You could really just take the bigger number minus the littler number, and then it's heading still in the direction of the bigger number, is really a way to think through it. For subtracting vectors, mainly the only thing we need to say is that it's really the same as adding and subtracting everyday numbers, integers. If you're going to subtract something, let's say u vector u minus vector v, well, that's really the same as vector u plus the opposite of vector v. And so being able to see it or use it in different ways like this helps us when we're drawing our diagrams and visualize it. But it's really the same as using regular numbers. And then you just have to pay attention to which direction the resultant is heading. Okay. The only other note that we need to take is on the zero vector. Okay, a zero vector occurs when you add two opposite integers. Zero vector occurs when we add two opposite vectors, or subtract two equal vectors, something like that, okay? So quick example would just be, you've got vector p and the opposite of vector p. And so when you add those up, p plus the opposite of p, you end up with the zero vector. The zero vector is written like this, okay? It has to be written as a vector because it's not just zero magnitude, it has a zero direction as well, as in it has no specific direction and the magnitude is zero. If we could draw a diagram of that quickly, all you would do then is you would take vector p, and then you would take the opposite of vector p and you would place it tail to head, and you'd head back to where you started, and then the resultant would be the zero vector, okay? All right, let's dig into some specific examples and draw some triangles and do some math here. In example 1, we are given a diagram of vector v and of vector u, and we are asked in A, there's going to be A and B, and we're going to do each of them a couple different ways so that we get used to it, but we're going to simply find u plus v. All right, well, one of the methods that we can use is the head to tail method, okay? Head to tail. What does that mean? Well, it means we're going to draw a vector u. Okay, we have vector u, and we are going to translate vector v so that its tail is at the head of vector u. So here's vector v. Okay, so the resultant now we draw from the tail of u to the head of v, and we have the resultant vector u plus v. Okay, all we're doing here is drawing that resultant vector. Well, what if we used the parallelogram method? The parallelogram method, or the head tail to tail method. Tail to tail, or parallelogram method. This was the triangle method over here. Okay, now what do we do? Well, now we stick them tail to tail. So I've got vector u heading down here, and vector v off like that. And what I need to do to complete my diagram then is to construct a parallelogram using vectors that are equivalent to vector u over here and to vector v over here. Okay? Now, the diagonal that begins at the tails of u and v and heads to the far corner of the parallelogram that we constructed. Again, if you're going to do it like this, you should probably use a ruler and actually get your angles right and your measurements right. I should just quick measure how long u is on my page so that I can translate it properly. But this resultant here then is u plus v. Okay, it's the diagonal of the parallelogram. Part B of example 1 asks us to find u, vector u, minus vector v. And there's going to be 3 different ways that we're going to do this. Okay, one of the ways that we're going to do this is the head to tail method, head to tail. So we're going to draw the opposite of v, which is negative v, and then we're going to translate it so that its tail is at the head of vector u, and then we can add them together. So what does that mean? Well, we're going to just draw a vector u, okay? And now, subtracting a positive is the same as adding a negative. So what I'm going to do is I see vector v here. I'm just going to give myself a negative v. Maybe I'll draw it up here. Okay, a negative v. Needs to be a little bit longer maybe. And now I'm going to translate that so that its tail is at the head of vector u. So now I've done vector u, and I'm going to do the opposite of vector v. Now that I have this, I can do it two ways. I can use the triangle method or the parallelogram method. And either way, what I end up with is a resultant vector from the tail of u to the head of v, and that is u, and I'm going to write it two different ways. I'm going to write it as u minus v. What we actually did, that's equal to the vector u plus the opposite of vector v. Okay? Again, we took the opposite of v, and then we did head to tail method. Basically like adding the opposite is what we did. All right, another option is to use the parallelogram option. So in that one, parallelogram, we're going to start the same way. We're going to actually do u plus the opposite of v, but this time instead of going head to tail, we're going to go tail to tail, okay? So we're going to take vector u, which looks like this, and we're going to take the opposite of vector v, which looks like this, and we're sticking them tail to tail, okay? Well, now when I complete my diagram, if I complete my parallelogram, I measure this out, make sure I'm doing something that looks relatively the same as vector v, something that looks pretty much the same as vector opposite of v. Sorry, this is the same as vector u. This is the same as opposite of v. And then I'm simply going to go from where my tails meet to where my new heads meet. And this is the resultant vector. It is u plus the opposite of v, or vector u minus vector v. All right, there is one more way to do this, and it is a tail-to-tail method. Tail-to-tail method, I'm simply going to take tail-to-tail method, and all we're going to do is we're going to take u as it's presented in the original drawing, and v as it's presented in the original drawing, and we're going to put them tail to tail. So here we have u, here we have v, and I'm now going to go from the head of v to the head of u. And I'm going to call that resultant vector w. Well, what happened here? W now is actually equal to negative v, because so I drew v heading from tail to tail, both heading the same direction, but then I drew my resultant from the head of v to the head of u. So what I'm actually doing is starting here, I'm tracing v backwards and then u forwards. So I'm actually doing the opposite of v and then adding the vector u. Okay? Well, this is the same as u minus v. Positive u, negative v. Okay? So we did a little bit different here, but then we just traced it backwards along v because we're looking for backwards along V, the opposite of V, and then forwards down U, and we ended up with the same thing. Now, my drawings aren't perfect, but you can see that my resultant vector in each diagram is pretty close to the exact same, okay? My original U and V here are a bit short, so that one didn't quite work out, but you should be able to see that whichever method you take, you end up with the exact same resultant, okay? 3 ways to do it: head to tail triangle, parallelogram, tail to tail triangle, going backwards along one of your vectors. One key when you're playing around with these diagrams and just learning about it and getting better at it is always think through and double check, okay, spatially, does that seem like what it should look like? Does that seem to make sense to me based on the first 2 vectors and what I need to do with them? All right, in example 2, we are given the diagram of a parallelogram. Take a second to draw that or something that looks like it. It's parallelogram EFGH. And the 2 diagonals are drawn, and the diagonals intersect at point J in the middle of our diagram there. What we're asked to do is consider 3 of the vectors, HF, FH, and GJ, and we're going to express each of those vectors as the sum of 2 other vectors. We're actually going to do it in 2 different ways. And then we're going to do the same problem with the same 3 vectors, but now express each of them as the difference of 2 other vectors. And we're going to do that for each of them in also 2 different ways. Okay, so let's look at FH. And there are a lot of possibilities for each vector here. We're just going to show a couple, but we're doing A, express each vector as the sum of 2 vectors, and we're doing it for 1, the vector HF. So we're going to take a look at HF. HF is the diagonal heading up here, and if we're looking at the sum of 2 vectors, then I would say we can look at HE and EF, and that would be the tail to head method. If we take the tail of EF and attach it to the head of HE, which it is, then vector HF is equal to vector HE plus vector EF. And that is, if we want to make a note of it, that is going to be the head to tail method. Head to tail. Okay, well, is there another way that we could get the vector HF? Sure, we can just head to these 2 vectors that are below, HG plus GF. HG plus GF, and that would be head to tail again. So I'm not actually going to write that one, but that is one option. Another option that we could do is we could actually add GF and EF. We could add EF and GF, and we could add those using the parallelogram method. So let me just write down what we're doing here. We're looking for expressing HF as a sum of 2 vectors. And we could do that by taking EF plus GF. And how would we do that? Well, you would draw these 2 vectors right there and right there, okay? And you could even put them like that. I guess what you would actually do is you would drag GF, you would drag the tail of GF to the head of EF, and you would end up with this going up that way, and the resultant vector would be the same as vector HF. Okay, so this is parallelogram method. All right, A, still working with the sum of 2 vectors. Now we're looking at FH, okay? So FH, vector FH is equal to, let's take a look at where FH is. Just redraw my diagram here so that it's not so confusing. Get rid of my extra blue lines. All right, FH is now the opposite of HF. See that? FH is the opposite of HF. So one thing we can actually do is really just add the opposites of the strategy that we use. Let's see if that works. If we are going from F to H, that's the same as going from F to E and then adding from E to H. See how that's the opposite there? So we're going from F to E and we're adding from E to H. Now, I could have also rewritten this as equals the opposite of HE plus the opposite of EF, but simply identifying if it's two letters, if you have the letter for the tail and a letter for the head, then all you have to do is swap those letters around and the tail becomes the head and head becomes the tail, and that's the opposite vector, okay? All right, another option, you can go ahead and think of another option for rewriting this as the sum of two vectors. You could even throw J in there, but we won't yet. But we could do, what did we already do? Let's do FG plus FE, right? FG plus FE, and again, that would be using the parallelogram method. You would take the tail of FE, add it to the head of FG, and you would end up going boom, boom. FH is the resultant. All right, number 3 for the sum is GJ. GJ is interesting because it's just a short part of the diagonal here. It's half of a diagonal coming from this corner up to the middle. And basically we're looking at paths that will get us from here to here through angle addition, or sorry, through vector addition. So we could add GH to HJ. And you can see how HJ is a vector that works essentially backwards back up to J. So we could say this is starting from G heading to H, and then add H heading to J. Okay, is there another path that we could use to get there? Certainly there is. We could maybe go up this way. We could go GF plus FJ. Remember, this is all addition. So you got GF plus FJ. That's good enough. Okay, let's head on to part B, where we're going to work with these same vectors, but this time we're going to express them as the subtraction or the difference of two vectors. And this is where you can either let your brain get all kerfuzzled, or you can just keep things organized. If we're doing the difference of two vectors, well, adding a negative is the same as subtracting a positive. All I would need to do here, if I see that I have HE plus EF, couldn't I subtract the opposite of EF? And that would be the same as adding EF if I subtract the opposite, if I subtract a negative. So watch what I can do here. I can just take HE, and then I can, instead of adding EF, I can subtract FE, the opposite of EF. What does that look like on our diagram? Well, we would have HE heading this way, and then we're going to subtract FE. So if I'm subtracting from here to there, that's the same as adding from here to there, which gets us the resultant vector HF. Okay? Another way we could do this, get the resultant vector HF, is to take vector GF and subtract vector GH. So we've got GF heading up this way, and if we're going to subtract vector GH, okay, we're subtracting it heading this way, which means we're actually adding it heading this way, which means that we could translate the tail of H to the head of F, and we'd end up with a resultant vector that looks like looks like that, looks a lot like HF, okay? Second one we're going to do, express FH, vector FH, as the difference between two vectors, and we're going to do it in two different ways. And let's see if we can figure one out just by looking at the diagram. Go ahead and try to figure one out. FH is heading back down this way. And so I could go down FG, and then I could add GH, but we're not looking at addition, we're looking at subtraction. So I'm going to actually subtract HG, the opposite of GH. Okay, so we've got FG, starting at F, heading down to G, and then I'm going to subtract the opposite of GH, which is HG. All right, and that will get us our resultant vector coming from F down to H. All right, let's see if we can do that another way. Probably can. Let's pick a vector that's like over here. Let's do it with, let's add, we need to subtract, but let's go start with FE. That'll get us down there. FE, so FH is equal to vector FE plus EH. So if it's plus EH, it could be minus HE. And that will get us a resultant vector FG. Now I could put FE minus GF. That would work. There's a whole bunch of different ways to get there. Okay. Let's look at our third friend here, which is GJ. And now we're expressing it as the difference of two vectors. GJ is this vector right here. So if we determined that it was GH plus HJ, then it could also be GH minus JH. GH minus JH. I'm just subtracting the opposite of the one that we did over here. Okay? Can we get there another way? Just by looking at the diagram. Let's see, we're going from here to here. So you can see that something like GF plus FJ would get me GJ. So I could take I could make one of those vectors its opposite and then subtract it. So if I maybe start with FJ as is, and then instead of adding GF, I'm going to subtract FG. Okay, so again, just looking at your diagram, seeing how you're getting to places, and then using opposite vectors to create subtraction sentences is a good way to start thinking about this. Example 3 gives us a bearing problem, and it's someone participating in an orienteering race. An orienteering race doesn't really have like a track or a path that you follow necessarily, but you're given a map and a compass and some checkpoints and some information, and you need to find your way through this unknown terrain. So somebody is participating in an orienteering race, it's you, and you walk 100 meters. I'm just jotting down some of the key information. 100 meters due east, then north 70 degrees east, you're going to walk 60 meters. How far are you from your starting position and at what bearing? So we're looking for a vector that says how far did you go and at one bearing. So we're going to use a drawing, and we're going to try to do our drawing to scale as best we can. Get out my trusty ruler here. And so we're going to head from our starting location, let's call it A here. We're going to head due east, and I'm going to say that 1 centimeter is 20 meters. So it's going to take me 5 centimeters to get 100 meters. We'll call that point C. Why? I don't know. But there we have our first thing. We're going 100 meters due east. And then from there, we're going to go north 70 degrees east. So what we actually need to do is we need to use a protractor. We need to give ourselves a vertical line for north. And we're going to continue our horizontal for east. Okay. And then we are going to use a protractor to accurately draw a diagram that allows us to head 70 degrees east from north. So I'm going to put this along the normal there, along the horizontal. North should be 90 degrees. My diagram's not perfect, but it's fairly close. And from north, 70 degrees toward east would get me to 20 degrees looking this way. And where this 100 meters translated into 5 centimeters, 60 meters then is going to translate into 3 centimeters. So there's my mark, there's my line, and there's 3 centimeters. Okay, this is now 60 meters. We've done it at an angle of 70 degrees from north to east. And we have this end point. So we have enough information here to draw our resultant. I'm going to do that in red. And we're coming from A to B. All right. So all we need to do now is measure the length of vector r, the resultant, and that will give us our magnitude. And then we're going to measure the angle A, CAB, and that will give us our direction. So first, the magnitude here. I'm at 8 centimeters. 8 centimeters. So the length, if I'm doing magnitude, right, I'm just taking the absolute value of r. It is 8 centimeters on my diagram, which represents, I need to multiply that by 20. So that's going to be 160 meters. This is kind of a silly example to do by hand because I shouldn't end up with 160 meters. The displacement here, the magnitude can't possibly be 160 because that would be if it was a straight line. So my measurement is off. Let's call it 7.8. And now 7.8 times 20, or 7.9 even. So it shows how accurate you ought to be with your diagrams. 7.9 centimeters, which multiplied by 20 is 158 meters. Okay, so there's our magnitude of our vector. And angle A then, if I measure with my protractor, stick my protractor with the dot here, right along that bottom line, and I get an angle of 7 degrees. Okay, angle A is 7 degrees, and that is relative to the east. So I was heading east and then up to the north. So I need to actually convert that to a quadrant bearing. I need to have that north heading toward the east. So yeah, let me explain that. This line is heading due east. We already know that. So I'm just going to draw my north line from A, north. And now I can see that from the north to my red vector, that's going to be 90 minus 7. It's going to be 83 degrees. Let me write that over here. Convert to quadrant bearing. So we're going to take that 7 degrees and subtract it from 90 degrees. And so that will show that rather than heading 7 degrees up from east, north toward the north from the east, in a quadrant bearing, which is what we've been given, so that's how we're going to give our answer back. We're going north toward the east 83 degrees. Therefore, angle A is north 83 degrees east. So you've traveled about 158 meters from your starting position at a quadrant bearing of about north 83 degrees east. If we could summarize that, let's just leave it as this. So you traveled 158 meters at a bearing of north 83 degrees east. Now, this is only one method. This is method one, kind of pen and paper, figure it out. But if you take another look at the triangle that we've now created with vector AC, CB, and AB, you have a triangle and you have two sides, and you actually know the contained angle here. You actually know this angle because it's a 90-degree angle, plus what we found out was a 70-degree angle. So if we have side, angle, side, if we have two sides in the contained angle, we actually have a trig method that we can employ, and it is the cosine law. So method 2 would be using cosine law. Once you've thought it through and you drew your diagram, you can take a look at any of the trig tools that you have in your toolbox that could be helpful. And we can say, since angle ACB, that's the angle contained, the obtuse angle contained in our triangle here, is 90 degrees plus 70 degrees equals 160 degrees, we can use the cosine law. So what are we trying to figure out then? The length of the last side. So the magnitude then of r squared is equal to, and again, we're not getting the direction here, we're just getting the magnitude. So the magnitude of angle r, the square of that is equal to the magnitude of AC squared plus the magnitude of CB squared minus 2 times the magnitude of AC times the magnitude of CB times the cosine of angle opposite the side, so angle ACB, the cosine of the measure of angle ACB. Okay, this looks fairly messy. I'm remembering all my arrows here, but it's just cosine law with the lengths of the triangle. If you really wanted to name the vectors, instead of naming vector AC, you could name it, well, you can't really name it vector R, but you could name them after the opposite angles in certain situations. But in this case, this way of naming it is most convenient. We could have called this vector AB on this side to be consistent, but we're using R because that means resultant vector. And now all I need to do is put in the values that I know. So AC is 100, take the square of that, 60 squared minus 2 times 100 times 60 times the cosine of 160 degrees. And that I would just click away in my calculator, and we would end up with, and then take the square root of it. So the magnitude of R after calculating that and then taking the square root of that answer is 157.7. Okay, which gives us an even more accurate answer than just drawing and measuring and guesstimating. That's going to be in meters. And then in order to find the angle A over here, this angle, all we would need to do then is use sine law, because we have now opposite information. We have the length of r and the angle opposite it, the measure of the angle opposite it, and we have the length of the side that is opposite the angle in question. So now to find angle BAC, use sine law to find the measure of BAC. And again, the information that we're looking for then is on top, the sine of angle A, over the opposite side length, which is CB. I'm just going to plug in my numbers right away. And then the completed ratio that we have is the sine of 160 degrees over the length of R, which we just found out is 157.7. All right, multiply both sides by 60. Take the inverse sine of both sides, and we end up with A, the measure of angle A, is equal to the inverse sine of 60 times the sine of 160 degrees over 157.7, which our calculator will tell us is about 7.5 degrees. And again, now we're in degree mode, hey, not radians, so make sure you double check your calculator. And again, that's relative to the east. It's heading this way, this angle right here, this little angle then is 7.5 degrees, okay? But we want it in quadrant bearings, so we're going to do the same thing. We're going to do 90 minus 7.5. So we get, therefore, 90 minus 7.5, which is 82.5, which tells us that we have traveled about 158 meters, 157.7 meters to be exact, at a quadrant bearing of north 82.5, so about north 83 east. Okay, two methods to use. All right, example 4, we're just asked to use our algebra skills to simplify things. If you look at these, they're not difficult at all. I can see that I'm going to have a u and opposite of u. That's going to create a 0 vector. And the only thing that's going to be left is the vector v. Okay, so that's going to be really easy. The answer here, the simplification here, is the simplified expression is just vector v. Okay, but in practicing and thinking through what we're doing with the properties of vectors and the properties that we already use of integers and things like that, I'm going to write some things down, some different steps. This one we'll do just without all the bonus steps, but here I'm going to kind of explain what's actually happening. So the first thing that we're going to do is we can apply the commutative property and add the opposite. So what I'm going to do is I'm going to use the commutative property of addition to write this as v plus u, and that's going to allow me to get the u's beside each other. So u plus v is the same as v plus u, and subtracting a vector is the same as adding its opposite. So I've got plus negative u here. Now, because I'm dealing with a vector plus a vector plus a vector, I don't need these brackets. Okay, so I'll rewrite it. But what I am going to do is I'm actually going to group my two opposite vectors, because that is going to create a 0 vector. So now what do I have? I have vector v plus the 0 vector, which is just vector v. Okay? And we already talked through that. We already know how that works. So over here, we're going to do it a little bit more quickly. What I would need to double check is that I don't have like a negative sign in front of a bracket that would be distributed to both of the vectors inside. I don't have that here. I do have a positive p vector and an opposite, a negative p vector, and I have a q vector and an opposite q vector. So, I mean, it's just the 0 vector at the end. Okay, these guys this guy cancels out this guy cancels out that guy, and we're left with the 0 vector. All right, that was lesson 6.2, addition and subtraction of vectors, working with triangles, parallelograms, trigonometry, all that good stuff. Sine law, cosine law coming into play, and then just basic algebra for simplifying vector expressions. Practice problems you should be able to handle from page 325, number 1 through number 13.